Hello everyone and welcome back. Now, in the previous video, we were introduced to second order differential equations. And in this case, we looked at linear homogeneous equations with constant coefficients. We saw that everything boiled down to solving a characteristic equation. That was a nice little quadratic polynomial, and we dig out the roots, and that gives us two distinct solutions to our linear differential equation. Now, what we're going to do in this video is we're going to zoom out a little bit and talk about the qualitative theory of these second order equations. So just like what we did with first order equations, we can ask ourselves, when do we have a solution and what is the largest interval that this solution is guaranteed to exist on? Now, I would like to start with a bit of a reminder. Remember that we were talking about second order equations that take this form. Now, they're linear. That means that y, the independent variable, and all of its derivatives appear linearly in this equation. This is going to be a homogeneous equation. That's why we have this equal to 0 here. And what we can do is we can actually abstract this just a little bit, and we can call this whole left-hand side a function, say L of y. So we can say that L of y, if you put a function y into this, then you get its second derivative plus p of t times its first derivative plus q of t times its just original function. Now, I know that this looks tedious, but the question is, why is it that we want to do this? Well, we like to do this because now I'm really looking for roots of a function, right? We're posing things in terms of mathematical problems that we are probably used to, right? Looking for roots of polynomials, for example. Well, we can say that solutions to this differential equation right here are roots of this abstract function L. Now, you should be very, very careful with this because L is in fact a function of functions, right? It takes in a function y and it returns, this sort of complicated looking formula back. So let me give you an example here first. Let's imagine p of t is equal to, say, t squared. And let's take q of t equal to, let's say, 1 plus t. So nothing too fancy here. I just want to use this for illustration. And what I can do is I can throw in a function. So let's say y of t is equal to, let's use sine of 3t. Again, everything is sort of arbitrary here just for illustration. But what happens if I put it into my function of functions? So we typically call these things operators. If I put this into my operator, I get L of sine of 3t. So when I put the function sine of 3t into this thing, I get first its second derivative. That is going to be minus 9 sine of 3t. And then I get p of t times y prime. So that's going to be plus t squared. And then the derivative of sine of 3t, well, that's just going to be 3 cos of t. So now I get 3, I'll put that in front of the t squared to make things look a little prettier, cos of 3t. And then finally, I'm left with q of t times y, which is leaving me with 1 plus t sine of 3t. So what is this trying to illustrate? It's trying to show you that I have a function of functions. So I say, I put in sine of 3t, I get this big, ugly looking mixture of sines and cosines and polynomials out of it. And the first thing that I want you to note is that thing surely does not equal to 0, and that tells me that I do not have a solution to my differential equation. Okay, so now let's start talking about some abstract theorems about existence of solutions to this differential equation. So the first theorem here, I'm going to give you an initial value problem. So I'm going to say, consider the IVP, initial value problem. And this is going to be Ly is equal to some function g of t. This can be an arbitrary function. It could be equal to 0, just like I have up here, or it could be equal to something else. And we saw already when it comes to initial value problems for second order equations, we actually need two initial conditions, one on the original function and one on its derivative. So I'm going to use the notation y naught and y naught prime to denote these initial conditions. So this is the abstract form that an initial value problem for a second order equation would come in. And in my case, I'm going to assume that P, Q, and G are continuous. So the same criteria that we saw previously for first order equations on, let's say, an interval alpha less than t, which is less than beta. So again, go back and compare what we've seen with first order equations. This should look a whole lot like it. And of course, this has to contain t naught, right? So we look for the largest interval of continuity where P, Q, and G are all continuous to the left and to the right of the value t naught. And we need that because this is where we have our initial condition. Well, then we know that there exists a unique, right? So that's what that exclamation mark here says. There exists a unique solution y equal to phi of t, so some function that exists for all alpha less than t less than beta, right? So again, it looks a whole lot like we've already seen with the first order equations. The only thing you need to do now is you need to check one other function is continuous as well for this to hold. So let's actually take a crack at an example here. So let's say, well, imagine I give you t squared minus 3t y double prime plus t times y prime minus, and let's say t plus 3 y is equal to 0. And let's assume that we are also given y of 1 is equal to 2 and y prime of 1 is equal to, let's say, 3. Now, the important thing that you should notice right away is that this is not in the form of these general second order equations that we've been talking about, and in particular those that apply to this theorem. Remember, L is defined from this original equation. So that means that I've got to divide off this leading order term here. And so really, my ODE should be written as y double prime plus, let's say, t over t squared minus 3t y prime plus, minus t plus 3 over t squared minus 3t y, which is equal to 0 again. Now you can see that I have it written in the correct form. I've got p of t right here. I've got q of t right here. And I actually have a homogeneous equation, but I still have g of t is just equal to 0 here. So the nice thing is that's one less condition for me to check, right? My g is 0, continuous everywhere, nothing interesting to really talk about. But let's talk about p and q. Now, technically, p has a factor of t that falls off. So p of t here is actually 1 over t minus 3. And q doesn't have any common factors. So in this case, q is still just t plus 3 over t squared minus 3t. Now, the way that I like to approach these problems is I like to draw a little number line and tick off or mark the regions where I have continuity of these functions. So let's say, here's my number line. Now, the first thing that I know is that p is not continuous at t equal to 3, right? It's a rational function. It's polynomial divided by polynomial. Its only problems are where you have singularities. So at t equal to 3, we've got a problem. Let's denote that right here. There's t equal to 3. Now, q also has some problems. It has a problem at t equal to 3, which we've already identified as a problem point for p, so we're okay with that one. But it also has a problem at t equal to 0. So let's mark that as another point on our number line. Now what we can see is that p, q, and g are continuous from minus infinity up to 0, from 0 up to 3, and from 3 up to infinity. So the real name of the game now is to identify where exactly our initial point puts us, right? Which one of these 3 intervals does our initial point put us in? Because remember, a very important criteria here was that we need to find the interval that contains t naught. Well, the first thing you can see here is that t naught is equal to 1. And so that means that t naught is going to put us, say, somewhere right here. And that means that I can go all the way to 3 if I go to the right with my solution, and I can go all the way to 0 if I go to the left with my solution. So this tells me, so therefore, my solution exists for all 0 less than t less than 3, right? So moving all the way to the left to get to the first problem point, all the way to the right to get to the next problem point. If you had p, q, and g that gave you way more headaches than that, then you would do exactly the same thing. You would write out your number line, identify all of the problem points, all of the discontinuities for p, q, and g, figure out where your initial condition puts you, and then throw yourself, see how far you can go to the left and to the right based on what that initial condition looks like. Okay, so this gives us existence of solutions. Now let's talk about something called the principle of superposition. So, principle of superposition. So again, we saw a version of this in the previous lecture. The principle of superposition tells us that if y1 and y2, so let's say if y1 and y2 are solutions of L of y, so there's my abstract way of writing my differential equation. Again, it's really just sort of a shorthand, right? It's just allowing me not to have to write this thing every single time I want to talk about it. But if I have 2 solutions to this, then so is any linear combination of these solutions. So this works for all C1 and C2 real numbers. Now, again, think about when we saw this last. We actually saw this in the previous lecture, right? Remember we said we had 2 distinct real solutions to our characteristic equation, say R1 and R2. That led to 2 solutions, e to the R1t and e to the R2t. And then I showed that we can mix and match those things. I can take a constant of e to the R1t, and I can add it to a constant of e to the R2t, and I still get a solution. That is the principle of superposition. That's exactly what this is saying, although this is doing it in a slightly more abstract setting. So this is actually a fairly easy thing to prove. So let's actually do the proof so that we can really understand what's going on here. So basically what I want to show is that L of C1 y1 plus C2 y2, I want to show that that thing is equal to 0. So let's actually write it out. So if I write L of C1 y1 plus C2 y2, well, again, I have a definition for L right here. So let's put it in. So if I take a second derivative of this thing, C1 and C2 are constants. So I get C1 y1 double prime plus C2 y2 double prime. Then I go plus P of t times the derivative of this thing. So same idea, C1 y1 prime plus C2 y2 prime. Now I've got plus Q of t C1 y1 plus C2 y2. Okay, so it's not so bad. I've got a lot of symbolic components here, but let's collect some like terms. So let's collect everything with the C1 in it first, okay? So I get C1, and from the first bracket I get y1 double prime. Then from the second bracket I get P of t y1 prime. And then from the last bracket I get Q of t y1. That's just all of the C1 terms going across this thing. Similarly, I get basically exactly the same thing from my collecting out the C2 terms. And hopefully you can see what's happening, right? Because look at what's inside of the brackets. This is now the differential equation evaluated at y1. So written sort of mathematically, this is L of y1. And the next one is L of y2. But here's the beauty of this. I know the value of L of y1 and L of y2 because I already said that if y1 and y2 are solutions, that means that they set this thing equal to 0, then this thing is a solution as well. So what happens here? C1 times 0 plus C2 times 0, which is equal to 0. So trace it all the way back up. What did I say? If I look at the very first line, L, remember my differential equation, evaluate at the function C1y1 plus C2y2. When I put that function in the differential equation, I get 0. But when it's equal to 0, I know I've got a solution to the homogeneous equation. And that gives me exactly what I'm looking for. Okay, so the principle of superposition is great, but it poses a little bit of an issue for us, right? Because what it says is that if you did your homework and I did my homework and we both came up with different solutions, then a third person could get another solution that takes both of ours and adds them together, and that could be theirs. So the question is, how do we know that we have sort of the right solutions here? Which ones are forming this sort of fundamental set of solutions? And the way that we quantify this is through what's called the Wronskian. Now, the Wronskian is, again, a sort of function of functions. So let's say, let y1 and y2 be solutions of, let's do it again, our abstract formulation of a differential equation, L of y is equal to 0. So then we define the Wronskian as, okay, so it's going to look a little ugly for a second. It's going to be a function, we call it W for Wronskian, y1 and y2. It's a function of functions. That means that its output is, again, a function of time. So this is a sort of weird notation that you might not be too familiar with. But this is to tell you that you get something in y1 and y2, and you get something out that depends on the time. So this is actually going to be a determinant of a 2x2 matrix. So it's actually going to be y1 times y2 prime minus y1 prime times y2, right? So this is actually just the determinant of this 2x2 matrix. So I'm using straight lines to denote the matrix. That's mathematical notation for a determinant. So remember, determinants are sort of forward diagonal. subtract the backwards diagonal when we just have a nice little 2 by 2 matrix. Okay, so the question is, where does this come from, right? What is this useful for? Why did I need to start talking about linear algebra and determinants when this is a class on differential equations? Well, here's the idea. So let's say idea. Let's say y1 and y2 are solutions of L of y equal to 0. Well, then the principle of superposition tells us that this thing, so any linear combination of them, C2, Y2 of t, is a solution too. All right, so that's the principle of superposition at work. Now, let's assume further that we're given, let's imagine that we're given initial conditions. So you tell me that you want to go through the point y0, and you want its derivative to go through the point y0 prime. Okay? So you give me these conditions. Then I say, okay, well, I can do this, right? I can put this together for you, because what does this actually do? Well, if I put these in, I get, so y at t0, so that gives me y0. And this gives me, so if I just put it into my big solution for any C1 and C2, remember that's the whole purpose of these C1 and C2s, is to tweak them in order to fit in order to fit initial conditions. So I get C1 times y1 of t0 plus C2 of y2 of t0. And I do the same thing with the derivative condition here. I got C1 y1 prime t0 plus C2 y2 prime t0. So, okay, you might still be a little bit confused, but let's keep walking through this. This is actually a linear system of equations for the unknowns C1 and C2, right? I have two equations, I have two unknowns. Let's pose this as a matrix. This is actually y0 prime is equal to y1 of t0, y1 prime of t0, y2 of t0, y2 prime of t0, and then multiplied against the unknown vector C1, C2, right? So this is a standard problem in linear algebra. AX is equal to B, and you need to solve for X. In this case, I need to solve for C1 and C2. And so the question is, when do I know that I have a solution no matter what the value of y0 and y0 prime are, right? So you could be interested in specific initial conditions. I could be interested in other ones. And so what we want to do is we want to ask ourselves, no matter what the initial conditions we get are, can we always guarantee that we can find C1 and C2 to put the solution together? Well, that would require this 2 by 2 matrix here to be invertible. Now, what is a condition for invertibility? Well, that its determinant is not equal to 0. So let's take a look at this. This is invertible if and only if its determinant is not 0, which we can take a look right here. Its determinant is actually the Wronskian at time t0. So what is the Wronskian telling us? Well, if the Wronskian at some point in time is not 0, it tells me that I can actually use y1 and y2 to build any solution to fit any initial conditions to my differential equation. That's what the Wronskian captures. It tells me a whole lot about the two candidate solutions that I was provided. Now, let's actually do this properly. So let's actually talk about a definition that comes from the Wronskian here. So let's say definition. Well, if the Wronskian of two solutions to a differential equation at some point in time does not equal to 0, so again, pull all of the knowledge back. That means that if it's not equal to 0, that this matrix is invertible. If this matrix is invertible, it means that I can find C1 and C2 to fit my initial conditions. That means that my differential equation, no matter what the initial conditions are, I can always find a solution that fits those initial conditions. Well, if this thing is non-zero for some T naught in R, then we say that y1 and y2, well, we say that these things form a, let's put this in a different color just so it really, really pops out. They form a fundamental set of solutions. Now, what does this really tell us? It says that y1 and y2, you can put linear combinations together in order to solve any initial conditions, right? So you've already got solutions to the differential equation. That came by assumption. What the Wronskian is telling you is whether or not you can actually get, or you can actually satisfy initial conditions. So let's take a look at an example here. Okay. So let's say consider, here's my differential equation. It's going to be 2t squared y double prime plus 3ty prime minus y is equal to 0. And also, we can see, or you can check that the square root of t and, let's say, 1 over t are solutions. And in this case, I'm going to restrict myself to t positive, so we don't have to worry about any singularities here, right? So if we apply the existence uniqueness theory, then p is going to be 3 over 2t, which has a singularity at 0. It's not continuous at 0. Q is going to be minus 1 over 2t squared. Again, singularity at 0. So we know from the existence of uniqueness theory from the first half of this lecture that solutions can't exist. They have to exist on either the right side of 0 or the left side of 0. In my case, I'm going to go with the right side just because I like positive numbers, but you could do the same thing for negative t as well. Now I'm telling you that I have two solutions. We want to check if they form a fundamental set of solutions. So let's put them into the Wronskian here. So y1 and y2 of t. Well, let's actually do the matrix formation, the determinant formation first. So this becomes y1, and then its derivative, 1/2 t to the minus 1/2. Then similarly, y2, t to the minus 1, and minus t to the minus 2. That's its derivative here. Now we have the sort of forward multiplication on the diagonals, subtracting off the backward multiplication on the diagonals. This is going to give me minus. Now I'm just in a case where I add the exponents here. So I get t to the minus 3 over 2. And then same thing, I get minus 1/2 along for the ride. And again, I get t to the minus 3 over 2. So I can put it all together. I can say that I have minus 3/2 t to the minus 3/2, which, as long as t does not equal to 0, this thing never equals to 0. In fact, actually, it's just never equal to 0. It just has a problem at t equal to 0. But then, so the Wronskian does not equal to 0 for all positive t, which tells me that y1 and y2 form a fundamental, F-U-N-D, set of solutions. All right, so that is exactly what my definition says. In fact, my definition says that all I need to do is find one value of t where this thing is not equal to 0. I don't have to talk about all of them. So in my case, you could take t equal to 1, t equal to pi, t equal to e to the pi, t equal to 1,000,000. Doesn't matter, right? All of those lead to a Wronskian that's non-zero, which from this definition right here tells us that the square root of t and 1 over t lead to a fundamental set of solutions to this differential equation. And again, just to zoom out, what is the purpose of all of this? It tells us that we can satisfy any initial conditions that you put on this equation. Okay, so what we've done is we've talked a lot about the theory of these things, okay? So what we're going to do in the next lecture is we're going to come back and we're going to start solving second order equations again. In particular, we're going to come back to that characteristic equation that was introduced in the previous lecture. We're going to ask ourselves, what happens if I get complex roots? What happens if I get a double root? How badly do things go wrong, and can I still solve these equations? So I'll see you in the next lecture.